What happens when a star falls asleep? Not in a violent supernova explosion, but in a gentle whisper, a slow dimming that takes longer than the universe has yet existed. Imagine a stellar ember so dense that a teaspoon of its matter would weigh as much as an elephant, yet so patient that it will shine softly for trillions upon trillions of years. Tonight, we venture to one of the cosmos's most serene and inevitable destinations. We're going to meet the white dwarfs, the peaceful ghosts of stars like our own sun, and witness the longest goodbye in the universe. To understand where we're going, we must first understand where these quiet embers come from. Picture a star very much like our sun, a yellow dwarf burning steadily for billions of years. For eons, it has balanced two cosmic forces in perfect harmony. Gravity wants to crush it inward, while the fury of nuclear fusion pushes outward. This delicate dance has kept it stable, warm, and luminous. But all dances must eventually end. The fuel that powers this stellar furnace is finite, and when the hydrogen in its core finally runs out, everything changes. The star enters the final chapter of its story. When the hydrogen fuel in the core is exhausted, fusion slows and then stops entirely. Without that outward pressure to resist gravity, the core begins to contract. It grows hotter and denser as it shrinks. Meanwhile, something remarkable happens in the shell of hydrogen surrounding the core. This shell becomes hot enough to ignite, and fusion begins there instead. The star suddenly has a new source of energy, but this energy comes with consequences. The increased heat from the shell causes the outer layers of the star to expand dramatically. Our once modest yellow dwarf begins to swell. Over millions of years, the star grows larger and larger. Its outer layers cool as they expand, shifting from yellow to a deep ruddy orange. The star has become a red giant. If this were our sun, its bloated surface would now engulf the orbits of Mercury and Venus, perhaps even reaching Earth. Yet despite its enormous size, the core continues to shrink and heat. Eventually, that compressed core becomes hot enough for a new kind of fusion to begin. Helium, the ash of hydrogen burning, now becomes fuel itself. Helium atoms fuse together to create carbon and oxygen in a brief but glorious second act. But for a star of this mass, helium fusion is the end of the line. Unlike more massive stars that can fuse heavier and heavier elements, our sun-like star cannot get its core hot enough to fuse carbon or oxygen. When the helium runs out, there is no third act. The core, now made almost entirely of carbon and oxygen, has nothing left to burn. Fusion ceases once again, this time forever. The star has reached its final crossroads. What happens next will transform it from a bloated giant into something far stranger and more beautiful. The stage is set for one of nature's most elegant transformations. The star is now in an unstable state. Without fusion to support it, the core contracts further and grows even hotter. Meanwhile, the outer envelope, barely held by the star's weakening gravity, becomes increasingly unstable. Powerful stellar winds begin to blow, carrying away the outer layers into space. These winds are gentle by stellar standards, but relentless. Over thousands of years, they strip away the envelope bit by bit. The star is literally losing its outer skin, exposing the hot, dense core beneath. This is not a violent death. It is a slow, graceful disrobing, like a dancer shedding layers at the end of a performance. As more and more of the envelope is lost, the hot core becomes visible. This core is incredibly hot, often exceeding 50,000 degrees or more. It bathes the expelled gas in intense ultraviolet radiation, causing it to glow with ethereal colors. The scene is now set for one of astronomy's most beautiful phenomena. You and I are about to witness the birth of a planetary nebula, a cosmic butterfly emerging from the chrysalis of a dying star. But remember, At the heart of this emerging beauty is something even more remarkable. The stellar ember itself, patient and eternal, is about to be revealed. The star has now fully entered its transformation. The vast majority of its mass, everything that once made up its outer envelope, is now floating away into the cosmos. These expelled layers contain the elements created during the star's lifetime, including carbon, nitrogen, and oxygen. They will eventually mix with interstellar gas and contribute to future generations of stars and planets. In a very real sense, dying stars like this one are the universe's great recyclers. But for us, the most captivating part of this scene is about to unfold. The planetary nebula is forming, and at its center, something ancient and patient is waking up. Let us pause here for a moment and appreciate what we're witnessing. The star that burned for billions of years is now gently releasing its outer layers into the cosmos. This is not an ending filled with violence or chaos. There are no shockwaves or cataclysmic explosions. Instead, there is only a serene, inevitable transformation. The star is becoming something new. At its heart, compressed by eons of gravity and heat, lies a core of carbon and oxygen so dense that a fragment the size of a sugar cube would weigh 1,000 kilograms. This is where our journey truly begins. We are about to meet the white dwarf. You and I now find ourselves surrounded by one of the universe's most delicate and beautiful creations. The planetary nebula spreads out around us in all directions, a glowing cathedral of gas spanning light years. Despite its name, it has nothing to do with planets. Early astronomers, peering through primitive telescopes, thought these objects looked like the disks of distant planets. The name stuck, but what we see now is far more wondrous. This is the ghost of a star, illuminated from within. Every wisp and tendril tells a story of the star's final years. Are you ready to explore this cosmic cemetery that is somehow also a birthplace? The gas around us shines because of the incredible energy pouring from the star at the center. The exposed core of the dying star is so hot that it emits vast amounts of ultraviolet light. This radiation is so energetic that it strips electrons from atoms in the surrounding gas. When these electrons recombine with atoms, they emit light at specific wavelengths, creating the brilliant colors we see. Oxygen glows green and blue. Hydrogen emits a deep red. Nitrogen adds shades of crimson and orange. The result is a palette of colors that no human painter could match. This nebula is not just beautiful. It is a testament to physics, to chemistry, to the fundamental processes that govern our universe. Each planetary nebula is unique, shaped by the star's rotation, magnetic fields, and the density of surrounding space. Some nebulae are nearly spherical, expanding outward in perfect symmetry. Others form hourglass shapes or bipolar jets or intricate spirals. The famous Helix Nebula looks like a cosmic eye staring back at us. The Ring Nebula appears as a perfect smoke ring in space. The Eskimo Nebula resembles a face surrounded by a furry hood. These shapes form because the dying star ejects its material unevenly. Fast winds collide with slower moving gas. Dense equatorial rings focus the flow into jets along the poles. The result is cosmic sculpture on an unimaginable scale. The planetary nebula phase is beautiful but brief. These nebulae typically last only 10 to 20,000 years before they fade and disperse. In cosmic terms, this is the blink of an eye. The gas continues to expand outward at speeds of tens of kilometers per second. As it expands, it cools and dims. Eventually, it will spread so thin that it becomes invisible, merging with the interstellar medium. But while it lasts, the nebula is a beacon. It announces to the galaxy that a star has completed its life cycle and that new material is now available for future generations. It is both a monument and a gift. Within this expanding shell, we can detect the elements that were forged inside the star. carbon created by helium fusion, nitrogen made through complex nuclear reactions, oxygen formed in the stellar core. Even small amounts of heavier elements are present. These materials are essential for life as we know it. Carbon is the backbone of organic molecules. Oxygen is what we breathe. Nitrogen is crucial for proteins and DNA. When you take a breath, you are inhaling atoms that were once inside a star like this. When you look at your hands, you are seeing matter that was forged in stellar furnaces. We are not separate from this process. We are part of it. But our attention must now turn to the star itself. At the center of this glowing cathedral sits the object we have come to see. It is no longer a red giant. It is no longer fusing elements. It is no longer even what we would traditionally call an active star. The outer layers have been completely blown away. What remains is the naked core exposed to space, radiating away its stored heat. This is the white dwarf, more dense beyond comprehension and destined to shine for an eternity. Let us approach it now. Let us see what becomes of a star when the fires finally go out, but the embers remain. As we draw closer, the white dwarf dominates our view. It is blindingly bright, shining with an intensity that seems impossible for such a small object. Its surface temperature can reach 100,000 degrees or more, far hotter than any normal star. It blazes with pure white or pale blue light. Yet despite this brilliance, the white dwarf is remarkably tiny. A typical white dwarf is roughly the size of Earth, containing perhaps 1/2 to 1.5 times the mass of the Sun compressed into a sphere just 12,000 kilometers across. Imagine all that stellar mass, all those quadrillions of tons of matter, squeezed into a ball no larger than our home planet. How is this possible? To understand the white dwarf, we must venture into the realm of quantum mechanics. This is where our everyday intuition breaks down and the universe reveals rules that seem almost magical. The white dwarf exists in a state of matter unlike anything we can create on Earth. It is held up not by heat or nuclear fusion, but by a quantum mechanical principle called electron degeneracy pressure. This pressure emerges from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When matter is compressed to extreme densities, electrons are forced so close together that this principle creates an outward pressure resisting further collapse. It is this pressure, not heat, that keeps the white dwarf from collapsing further under its own immense gravity. The white dwarf before us represents a perfect balance. Gravity wants to crush it smaller and smaller. Electron degeneracy pressure pushes back with equal force. The result is a stable, though incredibly dense, sphere. This balance will hold for trillions of years. Unlike a normal star, the white dwarf does not need fusion to maintain its structure. It has already completed its nuclear evolution. What we see now is essentially a cooling ember, a stellar corpse that will shine for eons simply by releasing the heat it accumulated over its lifetime. There is something deeply peaceful about this. The frantic nuclear fusion has stopped. The expansion and contraction have ended. Now there is only time, vast amounts of time, and a slow, gentle fade into darkness. Let us consider the size and scale of what we're observing. A white dwarf with the mass of the Sun would have a radius of about 7,000 kilometers. That makes it slightly smaller than Earth. Yet this object contains 330,000 times the mass of our entire planet. Think about that for a moment. All the oceans, all the mountains, all the rocks and metals that make up Earth multiplied by 330,000, compressed into a similar volume. The density is staggering. A typical white dwarf has a density of around 1 million grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Lead, one of the densest materials we encounter in daily life, has a density of about 11 grams per cubic centimeter. To truly grasp the density of a white dwarf, imagine holding a teaspoon of its material. That tiny amount of matter, just 5 milliliters, would weigh approximately 5 tons, 5,000 kilograms, as much as a large elephant. You could not lift it. It would fall through any floor, through any table, through the earth itself, until it reached the core. The gravity at the surface of a white dwarf is equally extreme. If you could somehow stand on its surface, you would weigh 350,000 times more than you do on Earth. The gravity would instantly crush you into a layer of atoms just nanometers thick. This is not a place for human visitors. This is a realm of extreme physics where matter behaves in ways we can barely imagine. The surface gravity of a white dwarf has another important effect. It creates an incredibly thin atmosphere, just a few meters deep in some cases. Any material on the surface is pulled down so strongly that it quickly stratifies by weight. The heaviest elements sink, while the lightest float to the top. As a result, most white dwarf atmospheres are pure hydrogen, with some showing pure helium instead. Heavier elements like carbon and oxygen, which make up the star's interior, remain locked deep below. This stratification happens over just a few days or weeks. It is as if the white dwarf is organizing itself, separating into perfect layers like some cosmic geology experiment. The result is a remarkably pure surface, often consisting of a single element. Some white dwarfs show evidence of heavier elements in their atmospheres, which seems to contradict this picture of stratification. How do these elements get there? The answer often lies in accretion. White dwarfs can capture material from space, either from passing asteroids, comets, or from companion stars if they exist in binary systems. When this material falls onto the white dwarf, it creates a temporary layer of contamination. Over time, this material will also sink and separate, but while it is present, we can study it. By analyzing the light from these white dwarfs, astronomers can determine what kinds of objects fell into them. We have found evidence of rocky bodies similar to asteroids and even signatures that suggest water-rich comets. In a strange way, white dwarfs become cosmic museums, preserving traces of the planetary systems that once orbited their progenitor stars. The white dwarf we are observing has no such complications. It is alone in space, surrounded only by the fading remnants of its planetary nebula. Its atmosphere is pure, its surface smooth and featureless. There are no storms, no sunspots, no prominences. The surface is simply a boundary between the interior and space, glowing white-hot from stored thermal energy. This star has entered what we might call its retirement. For billions of years, it burned hydrogen and helium, maintaining itself through fusion. Now it will spend far longer simply cooling down. And here is the truly remarkable part. The universe is not yet old enough for any white dwarf to have cooled completely. Every white dwarf that has ever formed is still glowing. They are all still in the process of fading. What will eventually happen to this white dwarf? Will it shine forever, or will it eventually fade to darkness? The answer is that it will fade, but the timescale is almost incomprehensibly long. A white dwarf cools primarily through radiation. It emits light and heat into space, slowly losing energy. As it cools, it grows dimmer and redder. Over billions of years, its brilliant white surface will shift to yellow, then orange, then red. Eventually, after trillions of years, it will become so cool that it no longer emits visible light at all. At that point, it will be a black dwarf, a dark, cold sphere of carbon and oxygen drifting through space. But we must emphasize this. The universe is only about 14 billion years old. The coolest white dwarfs we have observed are still thousands of degrees hot. No black dwarf has ever existed. Not yet. Before we move deeper into the cooling process, take a moment to appreciate where we are. You and I are observing a stellar remnant that contains no fusion, yet shines brighter than many active stars. We are looking at matter compressed to densities found nowhere else in the universe except in neutron stars and black holes. We are witnessing a form of quantum pressure that has no equivalent in our everyday experience. And we are seeing an object that will exist essentially unchanged for trillions of years, long after every star currently burning has also died. The white dwarf is a monument to the universe's patience. It is a reminder that not all endings are abrupt. Some things fade so slowly that the fade itself becomes eternal. To truly understand what keeps a white dwarf stable, we must dive deeper into the quantum world. You see, the white dwarf exists in a state that classical physics cannot explain. If we tried to describe it using only the physics known before the 20th century, we would predict that the star should collapse immediately under its own gravity. There would be no force strong enough to hold it up once fusion ceased. Yet here it stands, stable and serene. The answer lies in one of the most profound discoveries of quantum mechanics, a principle that emerges from the very nature of particles themselves. Let us explore electron degeneracy pressure, the invisible hand that holds up these dying stars. All matter is made of atoms, and atoms consist of nuclei surrounded by electrons. In ordinary matter, these electrons orbit their nuclei with plenty of space between them. Even in the densest materials on Earth, like osmium or iridium, electrons occupy discrete shells and orbitals, following well-defined quantum states. But in a white dwarf, the density is so extreme that electrons are stripped away from their parent nuclei. The matter becomes a plasma of nuclei, mostly carbon and oxygen, swimming in a sea of free electrons. These electrons are not bound to any particular atom. They move freely throughout the star. However, they are still governed by quantum mechanical rules. And the most important of these rules is the Pauli exclusion principle. The Pauli exclusion principle, discovered by physicist Wolfgang Pauli, states that no two identical fermions can occupy the same quantum state simultaneously. Electrons are fermions, and this rule applies to them absolutely. What does this mean in practice? It means that each electron in the white dwarf must have a unique set of quantum numbers. These numbers describe the electron's energy, momentum, and spin. When matter is compressed to white dwarf densities, the electrons are forced incredibly close together. They begin to fill up the available quantum states from the lowest energies upward. Eventually, all the low energy states are occupied. Any additional electron must go into a higher energy state, even if it means moving very fast. This creates a kind of quantum traffic jam. As more and more quantum states fill up, the average energy of the electrons increases. Remember, these electrons are not moving fast because they are hot. They are moving fast because the Pauli exclusion principle forces them to. Even if the white dwarf were cooled to absolute zero, these electrons would still be zipping around at relativistic speeds. This motion creates pressure. The electrons push back against any attempt to compress them further. This is electron degeneracy pressure. It is a purely quantum mechanical effect with no classical analog. It arises not from temperature, not from particle collisions, but from the fundamental nature of quantum particles and their requirement to maintain unique quantum states. This pressure is what holds up the white dwarf. The electron degeneracy pressure increases as density increases. The more you try to compress the matter, the more the electrons resist. This makes degenerate matter extremely stiff. It is far more resistant to compression than any normal matter. In fact, once matter becomes degenerate, it behaves more like a solid or a liquid than a gas. The white dwarf is sometimes described as a giant crystal or a cosmic diamond, and there is truth to that description. Despite its extreme temperature, the degenerate matter inside resists compression so strongly that it has many properties we associate with solids. It can support itself against gravity without needing thermal pressure. It maintains a fixed size determined by its mass and the laws of quantum mechanics. There is a limit to how much mass electron degeneracy pressure can support. This limit is called the Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar who calculated it. The limit is approximately 1.4 times the mass of the Sun. Any white dwarf more massive than this cannot be supported by electron degeneracy pressure alone. At such extreme densities, the electrons would be moving so fast that relativistic effects become important. The added mass would overwhelm the degeneracy pressure, and the star would collapse further. For stars that die with cores above this mass limit, the result is not a white dwarf but something far more extreme, a neutron star or a black hole. But for stars like our Sun, the remnant core is comfortably below the limit. It becomes a stable white dwarf held up by quantum pressure, destined to cool for eternity. The existence of white dwarfs is one of the clearest demonstrations that quantum mechanics governs the universe at every scale. These are not microscopic objects. A white dwarf contains the mass of the Sun and has a radius of thousands of kilometers. Yet its stability depends entirely on quantum principles that were discovered in laboratories on Earth. The Pauli exclusion principle, formulated to explain the behavior of electrons and atoms, turns out to also explain the final fate of stars. This is one of the most beautiful aspects of physics. The same laws apply everywhere. The rules that govern atoms also govern stars. Understanding the very small helps us understand the very large. We are all connected, from the quantum to the cosmic. As we drift away from the quantum realm and return to observing the white dwarf as a whole, remember what we have learned. This star is held up by a force that has no equivalent in our daily lives. It is stable not because it is hot, but because of quantum mechanics. Its density is so extreme that matter behaves in ways we can barely comprehend. And yet, despite all of this strangeness, the white dwarf is peaceful. It does not explode. It does not collapse. It simply exists, shining softly, releasing its heat into the void over timescales longer than the current age of the universe. There is something deeply calming about that. In a universe full of violence and chaos, the white dwarf is a place of stillness. Plunging. Now it will simply wait. Let us now examine the surface of the white dwarf in detail. What would we see if we could somehow withstand the crushing gravity and intense heat? The surface is remarkably smooth compared to a normal star. There are no convection cells, no granulation patterns like those we see on the Sun. The extreme gravity pulls everything down so tightly that the surface is almost perfectly spherical, with no features more than a few centimeters high. The atmosphere, if we can even call it that, is extraordinarily thin. On a white dwarf with a radius of about 7,000 kilometers, the atmosphere might be only 10 meters deep. Everything is pressed down, flattened, stratified into perfect layers by the immense surface gravity. The temperature at the surface can vary widely depending on the age of the white dwarf. A newly formed white dwarf can have a surface temperature exceeding 100,000 degrees Kelvin. At this temperature, it emits most of its light in the ultraviolet range, making it appear brilliant blue-white to our eyes. As the white dwarf ages and cools, its surface temperature drops. After 1 billion years, it might cool to around 20,000 degrees, appearing white. After 10 billion years, perhaps 10,000 degrees, appearing yellow-white. The cooling continues, but it is a very slow process. The white dwarf radiates away its internal heat, but because it is so dense and has so much thermal energy stored, the cooling takes an extraordinarily long time. Because the surface gravity is so strong, any atmospheric phenomena are dramatically different from what we experience on Earth or even on normal stars. If there were any turbulence or circulation in the atmosphere, it would be damped almost instantly by gravity. Everything falls. There are no rising convection currents strong enough to fight the gravity. The result is an atmosphere in hydrostatic equilibrium, perfectly stratified by composition. Hydrogen floats on top because it is lightest. If helium is present, it sinks below the hydrogen. Any heavier elements sink even further. This stratification happens on timescales of days. It is as if the white dwarf is constantly sorting itself, organizing its layers, maintaining its purity. Some white dwarfs exhibit mysterious variability in their light. These are called pulsating white dwarfs, or ZZ Ceti variables, named after the prototype star. The pulsations are not dramatic. The star does not change in size significantly. Instead, the pulsations are caused by sound waves traveling through the star's interior. Just as earthquakes on Earth produce seismic waves that tell us about our planet's internal structure, these stellar vibrations tell us about the interior of white dwarfs. Astronomers can study the frequencies of these pulsations and work backward to determine the composition, structure, and even the rotation rate of the white dwarf. It is a technique called astroseismology, and it has revealed much about these enigmatic objects. The white dwarf rings like a cosmic bell, and by listening to its tone, we can understand its nature. The surface of a white dwarf also has an extremely strong magnetic field in some cases. Magnetic white dwarfs can have field strengths millions of times stronger than Earth's magnetic field. These fields are remnants of the original star's magnetic field, compressed and amplified during the collapse. The magnetic field can affect the behavior of any infalling material and can channel particles into polar regions, creating localized hotspots. In extreme cases, these magnetic fields can be detected through their effects on light. The light from the white dwarf becomes polarized, and spectral lines split into multiple components. Studying these magnetic white dwarfs helps us understand how magnetic fields behave under extreme conditions and how they evolve over stellar lifetimes. Despite all these fascinating details, the overall impression of the white dwarf's surface is one of stark simplicity. It is a featureless, glowing sphere. There are no storms, no eruptions, no changing weather patterns. The extreme gravity crushes all variation. The surface is hot but stable. It radiates heat steadily and predictably. In a universe full of complex, chaotic phenomena, the white dwarf stands out for its simplicity and its patience. It is not trying to do anything. It is not reacting to anything. It is simply existing, shining, and very slowly fading. There is a lesson here. Even in death, even after all the drama of stellar life, there can be peace. There can be calm. The white dwarf teaches us that endings do not have to be violent. They can be gentle, beautiful, and serene. Before we journey into the interior, let us take one last look at the surface. This boundary between the star and space is where the white dwarf interacts with the universe. It is where light escapes, carrying information about the star's composition and temperature. It is where any infalling material first makes contact. It is the interface between the quantum interior and the classical cosmos. And yet, for all its importance, the surface is vanishingly thin. Below this fragile boundary lies an interior unlike anything else in the universe. A realm where carbon and oxygen, the building blocks of life, exist under pressures and temperatures that transform them into something both familiar and utterly strange. Are you ready to descend? Let us dive beneath the surface and see what lies within. As we pass through the thin atmospheric layer and descend into the white dwarf, the conditions change rapidly. the temperature soars even higher. The density increases exponentially. We are entering a realm where normal chemistry has no meaning. The heat and pressure are so extreme that atoms cannot exist as we know them. Electrons have been stripped away from their nuclei. What remains is a plasma of bare atomic nuclei and a sea of free electrons. This is the interior of the white dwarf, a place governed entirely by quantum mechanics and the relentless pull of gravity. Here, the rules of everyday matter no longer apply. Welcome to the heart of the cosmic ember. The interior of the white dwarf is composed primarily of carbon and oxygen nuclei. These are the ashes of helium fusion, the final products of the star's nuclear burning. Carbon nuclei have 6 protons and typically 6 neutrons. Oxygen nuclei have 8 protons and 8 neutrons. These nuclei are packed incredibly tightly together, far closer than they would ever be in normal matter. Yet they do not touch. Even at white dwarf densities, there is still space between the nuclei. That space is filled with the electron gas, the degenerate electrons we discussed earlier. These electrons move freely, zipping between the nuclei at high speeds. They are what holds the star up. The nuclei, meanwhile, are arranged in a surprisingly orderly fashion. As the white dwarf cools, something remarkable happens in its interior. The carbon and oxygen nuclei begin to arrange themselves into a crystalline lattice, much like water freezing into ice. This process is called crystallization, and it represents a phase transition from a liquid-like plasma to a solid-like crystal. The nuclei lock into fixed positions, vibrating in place but no longer moving freely. This does not happen all at once. It begins at the center, where the density is highest, and gradually spreads outward over billions of years. Eventually, the entire white dwarf, except for the thin outer layers, becomes a giant crystal. A cosmic diamond made of carbon and oxygen, with a mass comparable to the sun floating in space. Is that not one of the most beautiful ideas in all of astronomy? The crystallization of a white dwarf releases latent heat, similar to how water releases heat when it freezes. This heat slows the cooling process. A crystallizing white dwarf actually brightens slightly and cools more slowly than expected. This effect has been observed. Astronomers have found white dwarfs whose ages and luminosities do not match theoretical predictions unless crystallization is taken into account. When they include crystallization in their models, everything lines up. This is a remarkable confirmation of our understanding of white dwarf physics. We predicted that these objects would crystallize based on theoretical calculations. Then we went out and found evidence that it actually happens. This is science at its best. Theory and observation working together to reveal the nature of reality. The crystalline structure of a white dwarf is not uniform. Carbon and oxygen have different atomic masses, and under the extreme conditions inside the white dwarf, they tend to separate. Oxygen, being heavier, sinks toward the center. Carbon, being lighter, floats toward the outer regions. The result is an oxygen-rich core surrounded by carbon-rich outer layers. This process is called differentiation, and it is similar to how Earth's interior separated into a dense iron core and a lighter silicate mantle. In both cases, gravity pulls the heavier elements downward while the lighter elements rise. The white dwarf, despite being a stellar remnant, behaves in some ways like a terrestrial planet. It has an internal structure. It has layers. It even has a composition gradient. It is a solid object, even if that solidity arises from quantum pressure rather than chemical bonds. At the very center of the white dwarf, the conditions are the most extreme. The temperature can still reach tens of millions of degrees even after the star has been cooling for billions of years. The density reaches its maximum, perhaps several million grams per cubic centimeter. The pressure is unimaginable. Yet even here, the electrons remain degenerate. They provide the pressure that keeps the core from collapsing. The nuclei, locked in their crystalline lattice, vibrate with thermal energy but cannot move freely. This is the final state of matter for a star like the Sun. Black hole, not a neutron star, but a crystal, a diamond in the sky, shining with the last remnants of heat from a long-dead fusion fire. The interior of the white dwarf is also incredibly hot for an extraordinarily long time. Even after billions of years, the core temperature remains in the millions of degrees. This heat is trapped by the overlying layers. The degenerate electron gas is an excellent conductor of heat, but the outer non-degenerate layers are not. Heat leaks out slowly, taking billions of years to reach the surface and radiate into space. This slow cooling is why white dwarfs shine for so long. They are not generating new energy. They are simply releasing the thermal energy stored in their interiors. It is like a massive heat reservoir, gradually draining over timescales that dwarf human comprehension. The white dwarf is patient. It has all the time in the universe. As we rise back toward the surface, passing through the crystalline interior and the transition zones, we carry with us a profound realization. The white dwarf is not truly dead. It is not inert. It is a dynamic object undergoing slow but inexorable changes. It is crystallizing. It is cooling. It is differentiating. It is evolving, just on timescales far longer than any process we are familiar with. In a sense, the white dwarf is the ultimate expression of patience and endurance. It survived the death of its parent star, will outlive every star currently shining in the night sky, and it will continue to glow faintly but persistently for trillions of years into the future. If there is a lesson here, it is this. Even after everything seems to end, existence continues. Changed, quieter, but still present. The cooling of a white dwarf is one of the slowest processes in the entire universe. To understand why, we must consider what it means for something to cool. Cooling is the transfer of thermal energy from a hotter object to a cooler environment. For a white dwarf floating in the near vacuum of space, the only way to lose heat is through radiation. It emits photons, particles of light, that carry energy away. The hotter the surface, the more energy it radiates per second. But as the surface cools, the rate of radiation decreases. The cooling slows down. It is a process that follows a curve, fast at first, then slower and slower as time goes on. The white dwarf will never truly reach absolute zero. It will simply approach it asymptotically over timescales longer than the current age of the universe. In the first billion years after its formation, a white dwarf cools relatively quickly. It may drop from 100,000 degrees to 20,000 degrees. The star shifts in color from blue to white. This is the fastest phase of cooling, though even this is slow by human standards. After the first few billion years, the cooling rate decreases dramatically. It may take 10 billion years for the star to cool from 20,000 degrees to 10,000 degrees. The curve becomes flatter and flatter. After 100 billion years, the white dwarf might be at a few thousand degrees, glowing dull red, barely visible. After 1 trillion years, it might be at room temperature, emitting no visible light at all. And still, it continues to cool, approaching but never quite reaching the ultimate cold of space. During this cooling process, the white dwarf passes through a sequence of spectral types, much like normal stars. When very hot, it is classified as type DAO or DO, emitting primarily in the ultraviolet. As it cools, it becomes a DA star if it has a hydrogen atmosphere, showing strong hydrogen absorption lines in its spectrum. It may become a DB star if helium dominates. Cooler still, it becomes a DC star, showing no strong absorption lines because the surface is too cool to excite atoms. Eventually, at temperatures below a few thousand degrees, the white dwarf would be classified as a very cool DC, or perhaps DQ or DZ if traces of carbon or metals are present. These classifications help astronomers catalog white dwarfs and estimate their ages. The cooler the white dwarf, the older it is. As the white dwarf cools and its surface temperature drops, the wavelength of its peak emission shifts to longer and longer wavelengths. A hot white dwarf emits mostly ultraviolet light. A cooler one emits visible light. A very cool one emits mostly infrared. Eventually, a white dwarf will be so cool that it emits primarily in the far infrared or even microwaves. At that point, it would be nearly impossible to detect without sensitive infrared telescopes. These cool white dwarfs are sometimes called black dwarfs, though technically a black dwarf should be defined as a white dwarf that has cooled to the point where it no longer emits significant radiation at any wavelength. No such object exists yet in the universe. The universe is simply not old enough. The coolest white dwarfs we have observed are still several thousand degrees and still glowing faintly. How long will it take for a white dwarf to cool completely? The answer depends on what we mean by completely. If we mean cooling to a temperature of absolute zero, the answer is infinite. It will never happen. Thermodynamics tells us that no object can reach absolute zero in a finite amount of time. But if we define a black dwarf as a white dwarf with a surface temperature below, say, 5 degrees Kelvin, then we can estimate a timescale. Current models suggest this would take on the order of 100 quadrillion years. That is 100,000 trillion years. For perspective, the universe is about 14 billion years old. So a white dwarf needs to exist for more than 7 million times the current age of the universe to become a true black dwarf. No wonder none exist yet. During this unimaginably long cooling phase, the white dwarf simply drifts through space. It no longer participates in the active life of the galaxy. It does not form planets. It does not nurture life. It does not interact with much of anything unless it happens to be in a binary system or passes near another object. It is a silent witness to the evolution of the cosmos. Around it, new stars are born and die. Galaxies merge. Black holes grow. The structure of the universe changes. But the white dwarf remains, cooling slowly, shining faintly, a monument to a star that died billions of years before. There is something profoundly moving about that. In a universe of constant change, the white dwarf is a touchstone of continuity. Sneers. It endures. White dwarfs are also cosmic clocks. Because they cool at a predictable rate, astronomers can use them to estimate ages. By measuring the temperature and luminosity of a white dwarf, we can determine how long it has been cooling. This tells us the age of the white dwarf. If we also know how long the progenitor star lived before becoming a white dwarf, we can estimate the total age of the system. This technique has been used to estimate the ages of star clusters, including globular clusters, some of the oldest structures in our galaxy. The coolest white dwarfs in a cluster must be the oldest, having formed from stars that died long ago. By studying these cool white dwarfs, we can peer back into the early history of the galaxy. The white dwarfs, in their patient cooling, have become keepers of cosmic history. Let us take a moment to reflect on what we have learned about the cooling process. A white dwarf begins its journey as a blazing, blue-hot core exposed by the ejection of a planetary nebula. Over billions of years, it cools and reddens, its light shifting from blue to white to yellow to orange to red. It dims gradually, becoming harder and harder to see. Its interior crystallizes into a giant diamond. Its atmosphere stratifies into perfect layers. And through it all, it continues to shine, releasing the heat stored from eons of nuclear fusion. This is not a story of sudden endings. This is a story of gradual, graceful transformation. It is a reminder that not all change is fast. Not all endings are abrupt. Sometimes, the most profound changes happen so slowly that they appear almost timeless. Not all white dwarfs live in isolation. Many exist in binary systems orbiting companion stars. These systems can lead to some of the most dramatic phenomena in all of astronomy. When a white dwarf has a close companion, particularly a red giant or another evolved star, material from the companion can flow toward the white dwarf. This material, rich in hydrogen or helium, spirals down onto the white dwarf's surface, forming an accretion disk. As the material falls, it heats up due to friction and the white dwarf's intense gravity. The disk glows brightly, often outshining the white dwarf itself. These systems, called cataclysmic variables, are laboratories for studying accretion, one of the most important processes in astrophysics. As material from the accretion disk falls onto the white dwarf, it accumulates on the surface. This accreted material is compressed and heated by the white dwarf's gravity. Over time, a layer of hydrogen or helium builds up. When this layer reaches a critical mass and temperature, something spectacular happens. Fusion ignites suddenly and explosively in the accumulated material. This is not the steady, controlled fusion of a main sequence star. This is runaway fusion, a thermonuclear explosion that blasts the accreted material back into space. The white dwarf brightens dramatically, sometimes by a factor of 10,000 or more. We observe this event as a nova. For a few days or weeks, the system blazes brilliantly, then fades back to its original brightness. The white dwarf survives unharmed. Novae are recurrent. After the explosion, the white dwarf resumes accreting material from its companion. Another layer builds up. Eventually, another nova explosion occurs. This cycle can repeat many times over thousands or millions of years. Some novae are observed to erupt multiple times within a human lifetime. These recurrent novae provide valuable data about the accretion process and the conditions necessary for thermonuclear explosions. Each nova ejects material into space, enriching the interstellar medium with processed elements. In a small way, novae contribute to the chemical evolution of the galaxy. They are not as prolific as supernovae, but they are far more common, occurring thousands of times per year in our galaxy alone. But there is a scenario far more catastrophic than a nova. If the white dwarf continues to accrete mass over millions of years and approaches the Chandrasekhar limit of about 1.4 solar masses, something very different happens. Remember, electron degeneracy pressure can only support a white dwarf up to this mass limit. If the white dwarf exceeds it, the pressure can no longer resist gravity. The star begins to collapse. As it collapses, the temperature in the core skyrockets. Eventually, the carbon and oxygen in the core reach the temperature necessary for fusion. Unlike a nova, which only affects the surface layers, this fusion ignites throughout the entire core. The result is a Type Ia supernova, one of the most powerful explosions in the universe. A Type Ia supernova completely destroys the white dwarf. The fusion of carbon and oxygen releases an unimaginable amount of energy. The star unbinds itself in a fraction of a second, blasting all of its mass into space at speeds of tens of thousands of kilometers per second. The explosion shines with the light of billions of stars for several weeks, then gradually fades over months. Type Ia supernovae are important for cosmology because they have remarkably consistent peak brightness. This makes them useful as standard candles for measuring cosmic distances. It was through the observation of distant Type Ia supernovae that astronomers discovered the accelerating expansion of the universe, a discovery that led to the concept of dark energy. The exploding white dwarf in its final moment helps us understand the fate of the cosmos itself. Not all white dwarfs in binary systems will end this way. If the accretion rate is too low, or if the white dwarf does not reach the Chandrasekhar limit before other processes intervene, it may never explode. Some white dwarfs in binaries simply continue to accrete and experience periodic novae indefinitely. Others may merge with their companion if the two stars spiral together due to gravitational wave radiation. The merger of two white dwarfs can also lead to a supernova if the combined mass exceeds the limit, or it may create a single, more massive white dwarf or even trigger the formation of a neutron star in rare cases. The outcomes depend sensitively on the masses of the two stars, their separation, and the rate of mass transfer. Binary white dwarf systems are rich with possibilities. Binary white dwarf systems also emit gravitational waves. These ripples in space-time are produced when massive objects accelerate. Two white dwarfs orbiting each other closely create a changing gravitational field that propagates outward at the speed of light. These waves carry energy away from the system, causing the two stars to spiral closer together over millions or billions of years. Eventually, they may merge. Gravitational waves from binary white dwarfs are one of the targets for future space-based gravitational wave detectors. By detecting and studying these waves, we can learn about the population of white dwarf binaries in our galaxy and throughout the universe. The white dwarfs in their silent orbits sing a gravitational song that we are only now learning to hear. As we leave the realm of binary systems and return to the solitary white dwarf, we carry an appreciation for the diversity of stellar end states. A white dwarf alone is a peaceful, cooling ember. A white dwarf in a binary can be a source of explosive energy, enriching the galaxy and teaching us about fundamental physics. Both scenarios are valid. Both are part of the cosmic story. The universe does not have just one way of doing things. It explores possibilities. It experiments. And in that experimentation, it creates beauty, whether in the form of a serene, solitary white dwarf fading over trillions of years, or in the brilliant flash of a nova, or in the cataclysmic explosion of a supernova. All of these are expressions of the same underlying physics, playing out in different contexts. All of them are wondrous. White dwarfs are not exotic curiosities. They are incredibly common. In fact, they represent the end state of the vast majority of stars in the universe. Any star with a mass less than about 8 times the mass of the Sun will eventually become a white dwarf. This includes our own Sun. It includes most of the stars you see in the night sky. Over 90% of all stars will end their lives as white dwarfs. Right now, in our galaxy alone, there are estimated to be tens of billions of white dwarfs silently cooling in the darkness between the stars. They are the ghosts of past generations, the remnants of stars that shone and died over the galaxy's 14 billion-year history. White dwarfs play a crucial role in the chemical evolution of galaxies. During their formation, when the planetary nebula is ejected, they return a significant fraction of their mass to the interstellar medium. This material contains elements that were created inside the star during fusion. Carbon, nitrogen, oxygen, and traces of heavier elements are all present in the expanding nebula. This enriched gas eventually mixes with interstellar clouds and contributes to the next generation of star formation. In this way, white dwarfs help to gradually increase the metallicity of the galaxy over time. Each generation of stars is slightly richer in heavy elements than the last, thanks in part to the contributions of dying stars and the nebulae they leave behind. White dwarfs are also used as probes of fundamental physics. Their extreme conditions allow us to test theories in regimes that cannot be reproduced in laboratories. The behavior of matter at white dwarf densities helps us understand quantum mechanics and the equation of state of degenerate matter. The cooling rates of white dwarfs test models of heat transfer and radiation. The pulsations of variable white dwarfs probe their internal structure. Even the rate at which white dwarfs cool can be used to constrain the properties of exotic particles like axions or other hypothetical dark matter candidates, which could carry away energy and affect cooling rates. White dwarfs are not just fascinating objects in their own right. They are tools for exploring the fundamental nature of reality. In recent years, astronomers have discovered that some white dwarfs have planetary systems. These planets are the survivors of the star's red giant phase. When the star expanded, it likely engulfed and destroyed inner planets. But planets that were far enough away survived, though their orbits may have been altered. As the star shed its outer layers and became a white dwarf, these planets remained in orbit. We have detected planets around white dwarfs through various methods, including transits and the detection of metal pollution in the white dwarf's atmosphere. These systems are fascinating. They show us what the solar system might look like billions of years in the future, after the sun has become a white dwarf. Earth will likely be destroyed, but the outer planets may survive, orbiting a dim, cooling ember where the sun once blazed. Could life exist around a white dwarf? This is a question that has intrigued astronomers. At first glance, it seems unlikely. A white dwarf emits far less energy than a main sequence star. For a planet to be warm enough for liquid water, it would have to orbit very close to the white dwarf, perhaps closer than Mercury orbits the sun. At such close range, the planet would be tidally locked, with one side always facing the star. The conditions would be extreme. However, some studies suggest that if a planet could survive the red giant phase, or if it formed or migrated inward after the white dwarf formed, there might be a brief window, perhaps a few billion years, during which conditions could support life. It is speculative, but the universe has surprised us before. White dwarfs might host the last refuges of life in ancient star systems. White dwarfs also serve as cosmic fossils. Their properties preserve information about the stars they came from. By studying a white dwarf's mass, composition, and cooling age, we can infer the mass, lifetime, and even some characteristics of the progenitor star. White dwarfs found in globular clusters help us determine the ages of those clusters. White dwarfs in the galactic halo tell us about the early generations of stars that formed when the galaxy was young. White dwarfs in the disk trace more recent stellar populations. Each white dwarf is a piece of the puzzle, a clue to the history of star formation and evolution in the Milky Way. By studying them collectively, we reconstruct the story of our galaxy. Despite their importance, white dwarfs are often overlooked in popular discussions of astronomy. They lack the drama of supernovae or the mystery of black holes. They do not create stunning nebulae like active stars. They are small, dim, and quiet. Yet in their quietness they hold profound truths. They teach us about the fate of most stars, including our own sun. They show us that endings can be gentle and beautiful. They demonstrate that even in death, stars continue to exist, to shine, to contribute to the cosmos. White dwarfs remind us that the universe is not only about spectacular explosions and exotic phenomena. It is also about patience, about long, slow processes that unfold over timescales we can barely conceive. In that patience there is wisdom. As we contemplate the role of white dwarfs in the galaxy, we realize that they are everywhere and nowhere. Everywhere because they are so numerous and because they are the inevitable end state of common stars. Nowhere because they are so faint and small that most go unnoticed. They are the silent majority of stellar remnants, shining dimly in the background while other, more flamboyant objects capture our attention. But for those who take the time to look, who seek them out with telescopes and study them with spectroscopes, white dwarfs reveal a universe of complexity and beauty. They are worth noticing. They are worth understanding. They are, in their own quiet way, as magnificent as any supernova or galaxy. Perhaps more so, because they endure. Let us now turn our gaze to the far future, to timescales so vast that they challenge our comprehension. We have seen that white dwarfs cool slowly, taking trillions of years to fade from brilliant blue-white to dull red. But what happens when the cooling continues? What is the ultimate fate of these stellar embers? The answer is the black dwarf, a theoretical object that has never been observed because the universe is not yet old enough for any to exist. A black dwarf is simply a white dwarf that has cooled to such a low temperature that it no longer emits any significant radiation. It becomes invisible, a dark, cold sphere of carbon and oxygen drifting through space. This is the final state of stars like our Sun. How long will it take for white dwarfs to become black dwarfs? As we mentioned earlier, current estimates suggest timescales on the order of 100 quadrillion years, or 10 to the 15th power years. To put this in perspective, the universe is currently about 14 billion years old, or 1.4 times 10 to the 10th power years. That means white dwarfs need roughly 7 million times the current age of the universe to cool to the point of becoming black dwarfs. This is a timescale so long that it makes the entire history of the universe so far seem like the blink of an eye. By the time black dwarfs form, the universe will be a vastly different place than it is today. All the stars we see will have long since died. What will the universe look like in that distant future? Star formation will have ceased long before. The era of starlight, the cosmic epoch we currently inhabit, will be over. All the hydrogen and helium gas that fuels star formation will have been either locked up in stars and stellar remnants or expelled from galaxies by various processes. The last stars will have burned out trillions of years before the first black dwarfs form. The universe will enter what cosmologists call the degenerate era, a time when the primary inhabitants of the universe are stellar remnants like white dwarfs, neutron stars, and black holes. The universe will be dark, lit only by the faint glow of cooling white dwarfs and the occasional flare from matter falling into black holes. Even black dwarfs will not last forever. On timescales that make their formation time seem short, quantum tunneling effects could allow the protons in black dwarf matter to decay into lighter particles. This is highly speculative and depends on physics beyond the standard model. But if protons are not absolutely stable, then eventually even black dwarfs will evaporate, particle by particle, until nothing remains. The timescale for proton decay, if it occurs at all, is thought to be at least 10 to the 36 power years, possibly much longer. Alternatively, quantum fluctuations might eventually cause black dwarfs to tunnel to lower energy states, converting them into neutron stars or even black holes in events that would release enormous energy. These processes are so slow and so uncertain that we can barely call them predictions. They are speculations based on our best understanding of physics. Another fate awaits white dwarfs and black dwarfs over even longer timescales. Gravitational interactions with other objects will occasionally occur. A black dwarf might pass near another object, exchanging energy and momentum. Over unimaginably long times, these random encounters could eject black dwarfs from galaxies or cause them to fall toward the galactic center. In a process called dynamical relaxation, the structure of galaxies themselves will eventually dissolve. Some black dwarfs will be flung into intergalactic space. Others will spiral inward and be consumed by supermassive black holes at galactic centers. The time scale for this process is on the order of 10 to the 20 power years for significant changes. By then, galaxies as we know them will no longer exist. They will be replaced by diffuse clouds of black holes, neutron stars, and any surviving black dwarfs. Black holes themselves are not eternal. Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near their event horizons, a process called Hawking radiation. This causes black holes to very slowly lose mass and eventually evaporate. A solar mass black hole would take about 10 to the 67 power years to evaporate. Supermassive black holes would take far longer. When the black holes finally evaporate, the universe will enter its final era, sometimes called the dark era. By this time, even the photons from the cosmic microwave background will have been stretched by the expansion of the universe to wavelengths larger than the observable universe itself. The universe will be cold, dark, empty, and unimaginably vast. Nothing will remain except possibly fundamental particles like electrons, positrons, neutrinos, and photons drifting apart forever. Why do we contemplate these distant futures? Why consider timescales that make the current age of the universe seem like a fleeting moment? Perhaps because it puts things in perspective. Our lives, our civilizations, even our sun and planet, exist in a brief, bright interval in cosmic history. We live in the era of starlight, when the universe is full of energy and structure. This era will not last forever. Eventually, the stars will go out, the white dwarfs will cool, and the universe will fade. But that is not a reason for despair. It is a reason to appreciate the present. We are fortunate to exist in a time when the universe is alive with light and motion. We can look up and see stars. We can study their lives and deaths. We can understand, at least in part, how the cosmos works. White dwarfs and their future descendant black dwarfs are symbols of endurance. They outlast almost everything. They will shine long after every star currently burning has died. They will persist as silent witnesses to the aging of the cosmos. And even when they finally fade to darkness, in a universe defined by constant change, white dwarfs and black dwarfs represent a kind of permanence, or at least the closest thing to permanence that physics allows. They remind us that even as things end, something remains. Change is inevitable, but existence is resilient. The universe does not simply disappear. It transforms slowly and patiently over timescales that humble the imagination. Let us bring this story home, literally. Everything we have discussed applies directly to our own sun. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin its transformation into a red giant. It will swell to perhaps 100 times its current size, engulfing Mercury and Venus. The Earth, if it survives at all, will be scorched and lifeless, its atmosphere and oceans stripped away by the dying star's heat and wind. The sun will spend several 100 million years as a red giant, fusing helium in its core, then shedding its outer layers in a planetary nebula. What remains will be a white dwarf no larger than Earth, cooling slowly in the darkness. This is the future written in the laws of physics. But this fate is billions of years away. For now, the sun is stable, middle-aged, burning steadily in the prime of its life. It provides the warmth and light that makes life on Earth possible. It will continue to do so for billions of years yet. By the time the sun becomes a red giant, life on Earth as we know it will have long since either perished or evolved into something unrecognizable, or perhaps humanity will have spread to other stars. The death of the sun is not something we need to fear. It is simply a reminder that all things, even stars, have lifespans. The sun has been here for 4.5 billion years. It will be here for 5 billion more. And then it too will join the countless white dwarfs cooling silently in the galaxy, a monument to the star that once nurtured a world of life. What will the sun's white dwarf be like? Based on our understanding of stellar evolution, it will be a DA-type white dwarf with a pure hydrogen atmosphere. Its mass will be roughly half the sun's current mass, with the rest having been lost in the planetary nebula. Its radius will be about the size of Earth, perhaps 7,000 kilometers. Its initial surface temperature will be around 100,000 degrees, blazing brilliant blue-white. It will be a beautiful object, though far too faint to be seen from Earth's location without a telescope, assuming Earth still exists. Over billions and trillions of years, it will cool, shifting through white, yellow, orange, red, and eventually fading into a dark, cold black dwarf. The sun's light, which has shone for billions of years, will finally fade into silence. The outer planets of our solar system will likely survive the sun's red giant phase, though their orbits may be affected. Jupiter, Saturn, Uranus, and Neptune will continue to orbit the white dwarf, now receiving only a fraction of the light and heat they once did. Their moons, once warmed by the sun, will freeze solid if they were not already frozen. The asteroid belt and Kuiper belt will remain, orbiting silently. The solar system will become a graveyard, a collection of cold worlds orbiting a dying star. But it will persist. The structure will remain. The planets will continue their ancient orbits, governed by gravity, indifferent to the fact that their sun is now just a fading ember. There is something poignant about that. Even in death, the system holds together. Could future civilizations witness this transformation? It is possible. If humanity or our descendants survive for billions of years, they would have ample warning of the sun's death. They would see it gradually brighten and heat up over hundreds of millions of years. They could evacuate Earth, colonize other star systems, or perhaps engineer solutions we cannot yet imagine. They might even stay to watch from a safe distance as their home star undergoes its final transformation. They would witness the formation of a planetary nebula, the birth of a white dwarf, and the long, slow cooling that follows. It would be the end of an era, the closing of a chapter in the story of our solar system. But it would not be the end of the story itself. Life and intelligence, if they persist, will continue elsewhere. The sun's transformation into a white dwarf is not unique. It is the fate of most stars in the galaxy. Billions of stars will follow the same path. Each will live its life, burn its fuel, expand into a giant, shed its outer layers, and leave behind a white dwarf. The galaxy will gradually fill with these cooling embers. In the distant future, white dwarfs will be the most common stellar remnants, outnumbering all other types of objects. They will be the silent witnesses to the golden age of the galaxy, the era when stars shone brightly and planets formed and life perhaps flourished. When the last star finally dies and the last white dwarf cools to a black dwarf, the universe will enter a new phase. But that is so far in the future that it is nearly meaningless to us now. For now we live in the light. Contemplating the sun's future can evoke a sense of melancholy. Our home star, the source of all life and warmth on Earth, will eventually die. But there is also a kind of peace in this knowledge. The sun will not explode. It will not end violently. Its death will be slow, gentle, and beautiful. It will create a planetary nebula, a cosmic work of art visible across light years. It will become a white dwarf, a crystalline sphere of carbon and oxygen, shining softly for trillions of years. In its own way, the sun's death is as magnificent as its life. It is a transformation, not an ending. The atoms that make up the sun will persist, either in the white dwarf or in the nebula that spreads through space. Nothing is truly lost. Changes. For those of us alive today, the sun's death is unimaginably distant. It is 5 billion years away. Humans have existed for only a few 100,000 years. Civilization for only a few thousand. 5 billion years is a timescale beyond our capacity to truly grasp. Yet, knowing the sun's fate connects us to the cosmos in a profound way. We are not separate from the universe. We are part of it. The sun that warms our skin, that drives the weather, that powers photosynthesis and makes life possible, is a star like billions of others. It was born, it lives, and it will die. We too were born, we live, and we will die. We are connected by this universal pattern. We are all temporary expressions of matter and energy, existing briefly in the cosmic flow. And that is enough. We have journeyed far in this hour together. We have watched a star die and shed its outer layers in a planetary nebula. We have descended into the heart of a white dwarf and seen matter in a state that exists nowhere else in the universe. We have contemplated electron degeneracy pressure, the quantum force that holds these stellar embers aloft. We have watched the slow, patient cooling that will take trillions of years, longer than the universe has yet existed. We have seen white dwarfs and binary systems exploding as novae or supernovae. We have contemplated the far future, when white dwarfs become black dwarfs and the universe grows cold and dark. And we have brought the story home, considering the eventual fate of our own sun. What have we learned from all of this? Perhaps the most profound lesson is one of perspective. White dwarfs teach us that time operates on scales far beyond human experience. We measure our lives in decades, perhaps a century if we are fortunate. We measure civilizations in millennia. We measure geological time in millions of years. But white dwarfs measure their existence in trillions of years. They are patient beyond measure. They do not rush. They do not hurry toward any destination. They simply exist, cooling slowly, shining softly, waiting. In our fast-paced world, where everything seems urgent and immediate, the white dwarf offers a different wisdom. The wisdom of patience. The wisdom of accepting that some processes cannot be rushed. Some transformations take time, vast amounts of time, and that is perfectly natural. White dwarfs also teach us about endings. We often fear endings. We resist them. We try to hold on to things even when they are fading. But the white dwarf shows us that endings can be peaceful and beautiful. The star does not rage against its fate. It does not fight the inevitable. It accepts its transformation. It releases its outer layers in a glorious display of color and light. It settles into its final state with dignity. And then it simply exists, shining gently, releasing its stored warmth into the universe. There is no violence, no catastrophe, just a slow, graceful fade. This is a lesson worth remembering. Not all endings are disasters. Some endings are natural, necessary, and even beautiful. They make room for new beginnings. They complete a cycle. There is also a lesson about legacy. When a star becomes a white dwarf, it leaves behind more than just a cooling ember. It enriches the galaxy with the elements it created during its lifetime. Carbon, nitrogen, oxygen, and other elements are released into space through the planetary nebula. These elements mix with interstellar gas and eventually become part of new stars and planets. Some of these elements may even become part of living organisms on distant worlds. The star's legacy continues long after its active life has ended. In the same way, our actions have consequences that ripple forward in time. What we create, what we teach, what we contribute to the world does not die with us. It becomes part of the ongoing story of humanity and the universe. We all leave a legacy, whether we intend to or not. White dwarfs remind us of the interconnectedness of all things. The carbon and oxygen in a white dwarf were created by nuclear fusion inside a star. Those elements came from hydrogen formed in the Big Bang. That hydrogen was part of the primordial plasma of the early universe. The electrons that hold up the white dwarf through degeneracy pressure are fundamental particles that have existed since the first moments after the Big Bang. Everything is connected across space and time. The white dwarf is made of the same stuff as you and I. We are all stardust, quite literally. The atoms in your body were forged inside stars that lived and died before the sun even formed. You are a temporary arrangement of ancient matter, as is the white dwarf. We are cousins in the cosmic family. We are part of the same grand story. The existence of white dwarfs also highlights the power of scientific understanding. Just over a century ago, we did not understand what white dwarfs were. We did not know about quantum mechanics or electron degeneracy pressure. We did not know that stars had life cycles or that they ended in different ways depending on their mass. Now, we can predict the fate of any star with reasonable accuracy. We can describe the interior structure of a white dwarf in exquisite detail. We can calculate how long it will take to cool. We can detect them across vast distances and use them to probe the history of the galaxy. This is the triumph of human curiosity and intellect. We looked up at the stars and wondered. We asked questions. We built theories and tested them against observations. And slowly, patiently, we came to understand. If we can understand white dwarfs, we can understand anything. As our journey comes to an end, let us return once more to the white dwarf we have been observing. It floats serenely in space, no longer surrounded by the vibrant planetary nebula, now alone in the darkness. It glows softly, a patient ember in the cosmic night. It is neither alive nor dead in any conventional sense. It simply exists, a monument to the star it once was and a promise of the black dwarf it will eventually become. There is something deeply moving about this sight. In a universe that can seem chaotic and violent, the white dwarf is a place of calm. It has finished changing. It has reached its final state. Now it will simply wait, shining gently for longer than we can imagine. There is wisdom in that stillness. There is beauty in that patience. What does it mean to you, knowing that stars die this way? Does it change how you think about time, about endings, about your own place in the universe? The white dwarf asks nothing of us. It does not need our attention or our understanding. It will exist whether we notice it or not. But by choosing to look, by choosing to learn, we enrich ourselves. We connect with something far larger and older than ourselves. We participate in the grand narrative of the cosmos. We are fortunate to live in an era when we can understand these things, when we have the tools and knowledge to peer into the hearts of dying stars and comprehend what we see. We are witnesses to wonders that previous generations could only dream of. Let us not take that for granted. The white dwarf will outlive us all. It will outlive our civilization, our species, our planet, our sun. It will outlive every star currently shining in the night sky. Long after everything we know has faded into history and then into oblivion, the white dwarf will still be there, cooling slowly, shining faintly, waiting. And, in a strange way, that is comforting. The universe does not end when we do. Existence continues. The cosmos goes on, indifferent to our presence or absence, following its own immense rhythms and patterns. We are tiny and temporary, but we are part of something infinite and eternal. We are brief sparks in the cosmic fire, but we are sparks nonetheless. We burn brightly for a moment, and then we fade. And that is enough. That is everything. Our journey to the white dwarf is complete. We have witnessed the peaceful death of a star, the formation of a stellar ember held up by quantum forces, and the patient cooling that will take longer than the universe has yet existed. These sleepy, fading embers teach us about patience, about the beauty of endings, and about our place in the cosmic story. The next time you look up at the night sky, remember that among those points of light are countless white dwarfs, silent and serene, cooling slowly in the darkness. They are the monuments to stars that once burned as brightly as our sun. And one day, our sun will join them, becoming another patient ember in the eternal night. Until then, let us cherish the light we have. Thank you for joining me on this cosmic meditation. May you find peace in the knowledge that even as things end, existence continues. Sleep well, dream of stars, and remember that you are made of the same stardust that forms these celestial diamonds. Good night, traveler.